Olaf Chitil. His work making lazy contracts typed and practical.
Thank you. Well, we already heard that contract work of yours spinned off a lot of further work, and this is basically just yet another spin-off. And as you see from the title, I think the main focus is first on typed and lazy, and then in the end making it practical. Because first of all, you may wonder, well, if you're in a typed programming language, maybe why do we need contracts at all? We just express everything in the types. But actually, we do know that, at least in Haskell, we do have some limitations in the type system, and maybe actually we don't really want to express too much in the types because it just becomes too complicated then. So if you just want to look maybe here at this example, then we see here, basically we define here, a type of formulae here, propositional formulae, implication, conjunction, disjunction, and so on. And for these conjunctive, for these formulae, we now define a function called clausal normal form here. And well, let's first look at here at this function here, clausal normal form. We see that it takes a formula and it produces a list of formulae. And if we look at this type, it doesn't really tell us very much. You may think, well, this is really a bit of a strange function. First of all, why does it produce a list of formulae? Because the name suggests it produces a clausal normal form, so it produces literals as a result here. And also, another thing we will notice very quickly if we actually try to use this definition, that it doesn't work with any kind of formula. Actually, it expects the input to be in conjunctive normal form. Otherwise, this function may not even terminate when you execute it. Well, and that's exactly what we basically express here in the contract. So basically, in this line here, we connect to our old definition here, which is without contracts. We connect this kind of contract here, and we say, well, the whole thing is a function, yes, and the function takes as input something which is in conjunctive normal form, and it also actually has to be right bracketed. So if you have these associative operators, like for example, and, it always has to be in the right bracketed form, otherwise actually this function won't work. So this is really kind of precondition here for our clausal normal form function, and as a result here we see, well, it uses a list, but of literals here, not just any kind of formula, but there are only literals here. Yeah, we will actually see the definitions of all these other contracts like conjunctive normal form and right on a few other slides a bit later on. So that's kind of the aim that I'm looking for. Well, so let's look at all the individual aspects, because basically I had to look at lots of previous work and put things together. First of all, one thing that was very important for me is to produce a portable library, because I think anything about modifying an existing implementation is kind of hopeless to actually try that, because it's a lot of work and probably none of the implementers would be very keen actually to, for example, modify GHC to add contracts there. And I do know that, for example, for scheme and record, well, most of it is actually built there on the macro system, but in Haskell we don't quite have something as powerful as a scheme macro system, so I have to find a more simple approach there. Another important point is, well, I really want to stay within pure Haskell. I mean, in some previous work, actually, we used a couple of tricks here using unsafe perform IO, and well, first I thought everything is safe, you know, it's just used in a very safe setting there, but it turned out it actually did destroy some other properties, and so by just staying within pure Haskell, I'm very sure that nothing can go wrong by doing this. Another very practical point is here that all the types of our contract combinators really should be just have simple parametrically polymorphic types. I don't want to have any classes in there. The problem is when you just start adding contracts to an existing program and you have any kind of class context in your contracts, then suddenly these class contexts have to spread everywhere. You have to change types everywhere, and just terrible. So you really have to avoid doing that at all. And the big thing actually in Haskell is the semantic difference. We are working with a lazy language, and I really want contracts to preserve the semantics of the original program. If you add a contract and the contract actually does hold, then this contract should not change the semantics of the program at all. It should just be the identity, and nobody should notice about it. And naturally, if you work with any kind of partial data structures or infinite data structures, well, you cannot just evaluate somehow the whole data structure and test things there. No, that's not something we are allowed to do. So if you look here, maybe at this little example, if you want to basically assert that, well, this list here is actually a list of natural numbers, well, if we are using some kind of eager evaluation, well, we would just return an error here at this point. But in a lazy language, really we're not allowed to do that, because we may actually only look at the first element of the list. And well, the first element of the list is a natural number. That's perfectly fine. And in that case, we can really say, well, the whole program only saw a list of natural numbers. That maybe the second one is actually not one. That is not an issue. So that means that this error kind of only goes really in the position here. So for eager languages, basically, a contract is either the identity or returns an error. For lazy languages, it's more complicated because it may actually embed errors into the result here. Obviously, as functional programmers, we also want to have a nice algebra of contracts. I talked a little bit about adding some additional information to blaming. It turns out we can easily do that, which is very nice here. And finally, well, we do need some kind of data type dependent code in our contracts here. For every data type like lists or trees or whatever, there's something specific to that data type. But we want that code to be either easily written by hand, because we're just working with a library, or we want to have some simple mechanism here to do that. So, let's look at some example here. So, a very simple contract that you're probably all familiar with from other contract systems is just use some kind of predicate and use this predicate then to define a contract. So, prop turns a predicate here into a contract. So this is a contract over integers here. So basically this way we define our contract of natural numbers. Looking at a slightly bigger example here, we might, for example, want to say that the length function has a contract, while as a result the length function always returns a natural number, not any kind of integer. True is a contract which is always met. So that is quite convenient if you don't want to say anything specific there. True always holds. And well, if you introduce true, immediately the question comes up, well, what about the opposite, a contract that basically is never met? A contract called false. And you might think, well, is that pointless? I mean, a contract that is never met, I mean, what would that be good for in any way? Well, actually, in a lazy language, it can be useful, because basically if something is never being evaluated, well, that means that contract is basically never checked, and that means at that point it won't fail. And that is something we use here to specify a contract for the const function. So the const function takes two arguments here, a first argument and a second argument, and it always actually returns the first argument. And the second argument here is always ignored. Well, we can express that in our contract and say basically that the contract for this one is false. If const actually ever happened to evaluate that, then clearly something went wrong there. Okay, so that's a couple of very familiar contracts. Now maybe looking to some data structures, you might want to, for example, say that a list is infinite, which basically means that we never come across the empty list when we evaluate this list. And pconst, that is now a contract that is basically like a pattern for the const constructor of the list. So that says basically this is a non-empty list. The first list element, well, it's just true, so it's any list element, and the rest of the list is infinite again. So this way we have specified the infinite lists. Okay, so we have all that, and well, if you want to implement that, actually it's pretty trivial. It's very straightforward. We just look at the implementation of eager contracts from scheme. So just looking at that, the main idea is just that basically a contract, oops, there's a bit that, well, first of all, let's just look at here the API. So this is basically the API that I just used here in all the examples, and that's based on some previous works by Hinze and others here. But let's look at actually implementing this. So that's what we see here. So here we see that a contract, well, it's just a function from the type to itself. That's really what we expect, basically, because normally a contract doesn't change a value at all, and if it does, well, then it returns some kind of error.
And this implementation is straightforward. I mean, just looking at some examples. For example, here for the predicate here, well, we just check whether the predicate for the argument here is true or false. If it is true, well, then we return the value, else we return an error. There's one issue here with the predicate, and that's what's actually briefly mentioned in the previous slide, that I did actually introduce one class here, namely a class for flat data types. Because we can only do these predicate types really on flat data types in a lazy language, because then we can be sure, well, if we actually evaluate the predicate with the argument, well, there's no problem at all that there's still, I don't know, some sub-data structure that we evaluate too much. For flat data types, that's fine. But for anything like lists and so on, we should never actually use our predicate contract here at all. But yeah, so that's all pretty straightforward. I mean, true and false are pretty straightforward. Even here for conjunction, it's quite nice. Conjunction just means we apply both of our contract functions here, one after another here. And also for the patterns, it's pretty straightforward because we just do pattern matching. So for the null, well, yeah, if it is actually an empty list, we just return the empty list, so we adjust the identity. But if it is a non-empty list, well, then we have an error. So all this is very straightforward. That's something we already know. But there's a bit of a problem for data types. Namely, at the moment, I just specified the infinite list of types. But what if I want to do something more interesting? For example, I want to define the list of natural numbers. Well, in that case, I really need to have some kind of disjunction. I need to be able to express that a contract, something is either an empty list or it is a non-empty list here. So here, just looking at the example for natural numbers. So list of natural numbers here is either the empty list or it is a non-empty list where the first list element is natural number and the rest list are again a list of natural numbers here. So we need really some kind of operator like this. So this here is disjunction of contracts here. And that is really the problem here. What do we do with disjunction of contracts? And I thought about that quite a long time because our original representation doesn't work. Contracts just as functions from the element type to itself. There isn't really anything more you can do there. So you have to really find a different representation. And it turns out there's a very simple solution. And the solution is just that the contract type here returns not just the type itself, but it turns maybe that type. So it can actually now check whether the result is successful or not. So, because if you just return an error, there's nothing we can test there. But if we actually return nothing as a value, well, then we know that basically a contract failed, and the disjunction can actually check that. So if we just look here maybe at the definition of our disjunction here, so we see what we do is we just apply the first contract, and if the first contract actually is not successful, well, then we apply the second contract here. That's the idea of OR. And well, if the first contract is successful, well, that's great, then we just return the result of that one here. We don't even look at the original one. And that basically solves all our problems. It's quite amazing how simple it is. And just looking at a few other things here. So we notice that now we have lots of nice algebraic laws as well. I mean, that's something we would be all very keen. So let's check basically, we have conjunction and disjunction of contracts. Well, don't we expect that all the standard laws here of conjunction and disjunction of Boolean logic hold? Well, not quite. We have to be careful. I mean, lots of laws hold. So, I mean, for example, associativity holds, and true is the left and right identity here of the conjunction and so on. But especially conjunction and disjunction are not commutative. But in the end, for a lazy functional programmer, that's no surprise at all, because conjunction and disjunction for the Booleans is not commutative either. They evaluate from left to right. So it's exactly the same here. So it's quite nice that actually all the laws we get here for contracts are exactly the same laws that we get for conjunction and disjunction for our normal Boolean values. So we just have to look at them. And if we know that a certain law doesn't hold for Booleans, well, we can easily, from a counterexample, produce a counterexample here as well. So all these laws are really the ones you expect, and you basically can work with contracts just like you work with the Booleans, except maybe one point I should mention at this place here already, there's no negation. So you cannot have any kind of negation that leads to lots of semantic problems here. Here there are also some algebraic properties here for function contracts here. So you notice that basically, while if you have true for precondition and postcondition, then you can just use true itself here. So that's quite nice here. This law is actually a bit surprisingly complicated because the order here doesn't matter because conjunction is not commutative. So you have to be, if you really want to be precise here, careful about the order in here. And I know that some people sometimes get confused about function contracts. The symbol, although it looks like it, is not implication. It has nothing to do with implication. Actually, a function contract is more like a conjunction in many ways, because you're basically just checking that both the precondition and the postcondition hold. It's just they work on values of different types. Yeah, and then something else naturally we want to ascertain is that our contracts actually are projections. That's something we expect from contracts, and we can easily verify actually that they are partial identities. So basically they are either identities or they insert some errors into the result when the contract actually doesn't hold. And a second one, which I have to admit I still actually failed to really prove, although I'm very sure of it. Definitely it's not quite easy to prove this one here, is that assertions are actually idempotent, so if you apply the same assertion twice, it doesn't make any kind of difference there. But yeah, proving it definitely is a bit more complicated. Yeah, then just looking back at our original example, maybe seeing how we can define our contracts, just getting a bit more of a feeling for it, because we said, well, we have this kind of contract here for our clausal normal form. Well, we can define all the different parts here of our conjunctive normal form. So let's just start here. A conjunctive normal form is basically something combined with the and combinator here, so it's and of two conjunctive normal forms, or it's simply a disjunction here. And a disjunction is basically an or of some disjunctions, or it is a literal. And a literal, again, is just a negation of an atom, or it is just an atom by itself. And that's the atom. So all the contracts basically, they just read like data types. And that's in some way what you get, because you basically have a context-free description of contracts, and you basically get kind of a subtype of any kind of data type if you're just looking at algebraic data types. But you can do a little bit more here. So this one here is about the right bracketing here, and to express that some kind of formula is expressed in a right bracket form. Well, so let's say the outer one is an implication. Well, if the outer one is an implication, what we want is that basically the first argument, well, it should be right bracketed, but also the first argument should not have an implication at the top. And that is here what this additional combinator here expresses, that there's not an implication at the top. So you don't have general negation, but you can't check that there's not a certain data constructor at the top. Well, blaming is actually the same as for eager languages, and hence I won't really say anything about it. It was just trivial to add to it all. Then, as I said, we can actually add additional information, which is very nice. So, for example, if something fails here, so here we apply clausal normal form to some formula, which you don't even see here, and we get some kind of exception here, well, the error message actually tells us a bit more here. It tells us, well, it is kind of a function contract, and the argument here is of this form. It has an and on the outside, then an or inside, then a not inside, and inside the not is another not. And that is not allowed. Yeah, so that's what we see here. I think I won't say very much about this here. I mean, I use template Haskell actually to derive all these combinators. And I have to say, I looked at lots of generic programming packages there, but none of the other ones seem to be suitable because, first of all, many of them work with classes, and I don't want to have any classes, and second one, nearly all of them seem to be first order. The only thing they can usually do is maybe just recognize a function, but you can't do anything with a function. So they are pretty useless for this purpose here. Yeah, and that's basically the whole summary of what I've been talking about. The big challenge actually for the future that I'm still thinking about is, well, there are no dependent function contracts here. And I mean, I think in general that's probably not possible to combine this with laziness, but I do still think it should be possible to have a little bit in that direction. At the moment I put something in the implementation which basically does give you dependent function contracts, but it is not guaranteed to preserve the semantics. So you have to be careful when you actually use it, if it really gives you what you want, or if you actually modify your program. Thank you very much.